Hello everyone, my name is Diyu Yang. I'm a PhD student from Purdue University. Today, I'm going to present our work, Black Box Model Inversion using the Proximal maps. Map estimation is widely used in a lot of imaging applications. In a typical map inversion framework, we usually have a prior model, which is defined by some prior probability distribution P of X, and a forward model, which is defined by a conditional probability distribution P of Y given X. Map estimation tries to find the solution of the minimization problem f of x plus h of x with respect to x, where f and h are negative log likelihood of prior and forward model distributions, respectively. We can solve the minimization problem with ADM algorithm with variable splitting. For the prior and forward likelihood functions f of v and h of v, we define their associated proximal maps, capital F of v and capital H of v, as shown in the slides. We will talk about these proximal maps in detail in later slides. The minimization problem in previous slides can then be solved by iteratively applying prior proximal map and sensor proximal map until convergence. By replacing prior proximal map with any Gaussian denoisers, we have the so-called plug-and-play, which is a framework widely used in a lot of computational imaging applications. The idea of proximal map is that given an input x, the proximal map will return a better output x hat by projecting x onto the prior manifold or sensor manifold. In plug-and-play, we try to find a point that minimizes the distance between prior manifold and sensor manifold by iteratively applying prior proximal maps and sensor proximal maps. We have just seen that in plug-and-play, we can replace the prior proximal map with any Gaussian denoisers. However, we still need to compute the sensor proximal map. This creates a problem because for most forward models, sensor proximal map is either physically intractable or computationally expensive. In this presentation, we introduce the proximal map, an approximation of conventional proximal map of any given black box forward model. By black box forward model, we mean that the forward model is implemented as a standalone software system without a simple analytical form that can be used in inversion. The idea is that although we cannot mathematically compute the inversion of the black box model, we can approximate its associated sensor proximal map with a deep neural network. We start by defining the forward model as y equals to a of x plus w, where the function a is a black box forward model, is a black box forward projection model, and w is noise that follows some Gaussian distribution. In this case, we can write the log likelihood function f of x as the norm of y minus a of x multiplied by some scalar constant 1/2 sigma squared. We then express the proximal map as h plus v, where h is the residual between input v and the output f of v. We use a deep neural network to learn the residual h. Notice that the function h takes two input arguments, v and y minus a of v. The intuition behind this is that as the scalar term sigma squared goes to 0, we can approximate the residual f of v minus v as minus sigma squared times the gradient of f with respect to v, where the gradient term is a function of v and y minus a of v. We generate training data of the proximal map as follows. We take a typical input image v, and we generate x by assuming a synthetic prior model where x equals to v plus epsilon, where epsilon is added white Gaussian noise with variance sigma squared. We then throw X into our forward model and get the observation data Y. Then our deep neural network will take two inputs. One is V, the other one is Y minus A of V. And the network will be trained to estimate epsilon, the residual between input V and the ground truth X. The reason why we call this ground truth is that X is the image we used to generate the observation data Y. We use minimum mean square error as our training loss function, and eventually the deep proximal map is defined by H plus V. So how are conventional proximal map and deep proximal map related? The conventional proximal map is exactly the map estimate of X given Y and V. According to the way we generate deep proximal map training data in the previous slide, we can see that deep proximal map generates the minimum mean square error estimate of X given Y and V. Under many conditions, we would expect map estimation and minimum mean square error estimation to be approximately the same. Therefore, under reasonable conditions, we would expect that deep proximal map would be a good approximation of conventional proximal map. For the special case where forward model A is linear, we can compute an exact solution for conventional proximal map as shown in the slide. In this case, it is also known that map estimation and mean square error estimation will be exactly the same. Looking at the mathematical expression of conventional proximal map, we can see that now the residual part H only depends on one input, Y minus A of V. So in this case, we can drop the term V from the input of H and write H as H of Y minus A of V. Here's an example of a linear forward model application. In this model, we have input X to be a 512 by 512 high resolution image. We first filter X with a sinc anti-aliasing filter, and then downsample the output of the filter by 4 along each side of the image. Our output Y is therefore a 128 by 128 low resolution image. This is a very simple filter downsampling forward model. Here we have the neural network architecture for this particular forward model. We take a single input Y minus A of V. We use a 6-layer convolutional neural network to approximate the residual term H of Y minus A of V. We now compare the output of deep proximal map with the output of conventional proximal map, which is estimated by iterative coordinate descent. We see that for this forward model, the deep proximal map is pretty close to conventional proximal map because the error image is almost 0 everywhere. We then plug the conventional proximal map and deep proximal map respectively into the plug-and-play framework. The results of plug-and-play are very similar using conventional and deep proximal map respectively. This proves that for this forward model, deep proximal map is a pretty good approximator of the conventional proximal map. We now try to perform some actual reconstruction using deep proximal map. We have a nonlinear camera model A of X defined as in the slides. Our input X is a typical image. We first gamma uncorrect X by raising it to the power of gamma. We then apply a low-pass filter H to the gamma uncorrected image. We finally Gary correct the output of the filter H by raising it to the power of 1 over gamma. On the right-hand side, we have an example input image X and example output image Y. We can see that this cheap camera model introduces several kinds of artifacts. It blurs the input image and decreases the contrast of the input image. Since this is a nonlinear model, its proximal map is going to be very hard to compute. Can we replace proximal map with deep proximal map and form a good reconstruction? For this imaging application, we will use multi-agent consensus equilibrium framework for reconstruction. At this point, please allow me to take a slight detour and talk about MACE, because we're also going to use MACE later in another example. So MACE is a generalization of plug-and-play framework. We can view plug-and-play as a force balancing system between two agents. One agent is the prior proximal map, and the other agent is the sensor proximal map. Plug-and-play then try to reach an equilibrium point that balances out the tension between the two agents. MACE framework generalizes plug-and-play to the case where we have multiple agents associated with several forward models or prior models. The forward model agents are usually proximal maps, and the prior model agents are usually denoisers. MACE also introduces the scalar term betas to assign weights to different agents. The MACE framework is exactly equivalent to plug-and-play when one forward model agent and one prior denoiser agent is used, and the two agents are equally weighted. We now go back to our experiment. So here we use two agents for the consistent equilibrium framework. One agent is the prior model agent, which is implemented using a DNCN denoiser. And the other agent is a D-proximal map agent that we just seen in the previous slides that is associated with the camera forward model we have seen in earlier slides. We can see that with the help of D-proximal map, we're able to do a pretty good reconstruction. The reconstructed image removes most of the blurring artifacts and also increases the contrast of the image compared to Y, the output image of the camera model. We will now see a very interesting example where we train deep proximal map of a forward model, which is also another deep neural network. Here we have a forward model that is a MNIST classifier. The input image X is a 28 by 28 binary digit image, and the output is a 10 by 1 vector representing the classification result of our MNIST classifier. The architecture of the MNIST classifier is shown below. This model has a 98.1% test accuracy. Notice that this model is highly nonlinear because the output dimensionality, which is 10 by 1, is much smaller than the input dimensionality, which is 28 by 28. And therefore, the conventional proximal map would be very computationally expensive to compute. So now we will train the proximal map to invert this highly nonlinear neural network forward model. The architecture of the proximal map for the MNIST forward model is shown in the slide. This network is mostly consisted of CNN layers, except for the first layer of Y minus AOV input branch, where we use a fully connected layer to reshape the data from 10 by 1 to 7 by 7 by 1. We now take a single digit image and pass it into 4 different forward models. Forward model A is the MNIST classifier we've seen earlier. Model B is the row projector, which computes the average pixel values of the input image along horizontal directions. Model C is a column projector that computes the average pixel values along vertical directions. Model D is a block averaging function that calculates the average pixel values within each 4x4 block area. We can see that all of these models are quite simple. Model B, C, D mimics physical sensor models, while model A represents semantic data model of the input image. We will now use MACE framework to fuse these heterogeneous information together and form a single reconstruction of the original image. Our MACE framework consists of 5 agents. We have one prior agent, which is DNCN denoiser. For the 4 forward model we have 4 associated sensor agents. For MNIST classifier, we use its deep proximal map as the sensor agent. And for the remaining 3 models, we use their conventional proximal maps. Since these models are all quite simple, their conventional proximal maps can be mathematically computed. We now demonstrate our experiment results. On the left-hand side, we have reconstruction results of 4 different images with and without the deep proximal map agent for MNIST classifier respectively. We see that adding deep proximal map into Maze framework greatly enhances the reconstruction quality. We performed reconstruction across 1,000 test images. The average root mean square error across these test images are greatly reduced from 0.155 to 0.088 after adding deep proximal map agents into Maze framework. In this presentation, we introduced deep proximal map. Deep proximal map can be accurately approximate conventional proximal map for linear forward models. It is a powerful tool for inverting a wide range of black box models. It can also help Maze to fuse heterogeneous information together and form better reconstructions. Thank you.